2 of part 1. As weird as that sound, I accidentally stopped the part 1 video, so I'm going to have to do this last bit in the second part, maybe for about 5 and no more than 10 minutes. So this is the next slide from the previous part. So we're going to talk about why it's not possible to compute mean differences for more than 2 groups, 3 or more, using T and Z tests, and why we can use the F ratio to do such comparisons. So when you watch this slide, and as we talk about it, here are 2 pointers. One, we need to figure out why it's not possible to figure out one sample mean difference between more than 2 samples. Remember the thing we talked about. And the possibilities in which the ways that the means could be different. It could be just between mu1 and mu2. It could be between mu2 and mu3. So that's already 2 possibilities. It could also be mu1 and mu3. So that's 3 possibilities that is different. Or it could be all of them. So that's 4 possibilities. Okay, so therefore we need something else. We need something better for multiple mean comparisons, which is why we have the F ratio. Instead of comparing means, we are looking at variances rather than sample means. This means that we are looking at between group variances, here, that's in the numerator, over the variances or differences within the groups when there is no treatment. Again, think of this as individual differences that already exist. Okay. So again, we have the numerator and the denominator. So this whole bit here is like one giant F ratio. Again, F is between group variances over within group variances. So that's this slide. This is the last bit, I think, and I'm going to double check very quickly. Yes, this is the last bit for part 1. And we're going to use this slide to explain the number one, the key reason why we can't use more than one t-test, multiple t-tests to compare more than 2 means. This is called the idea of experiment-wise type 1 error, when we add up all the possible type 1 errors in different t-tests. So here we go. Remember, let's start with, 3 means. Here we have mu1, mu2, and mu3. Okay? And so, using our factorial design, remember back to that 2 by 2 factorial design where one factor has 2 levels and the other one has 3 levels. And so multiplying 2 by 3 would give us 6. And we had to do 6 tests. We're measuring 6 groups. But if we do make our comparisons, it's going to be more than 6. With 3 groups, even with just one factor, we're going to make more than one pairwise comparison. So I'm going to draw it out here, maybe with a whiteboard. Let me try this out now. I'm going to erase the hello and bye-bye smiley face. So we're going to look at different pairwise comparisons. Okay. All right, so again, we start with our means. We're going to figure out whether the 3 sample means are equal. Okay, so again, we write them out. Not, no. Okay, so H naught is null hypothesis, or simply no. All right, so again, how many comparisons would we make if we only use t-tests? If we only use t, or you, in this case, we, use t-test. We would make at least one. Okay, mu1, okay, and equals mu2. So here, so it's h naught number 1. Okay, so I'll just use more numeral here. Okay, second pairwise comparison. Mu2 and mu3. Okay, that's one other comparison. And finally, okay, one more. 1 and mu3. So you may notice with 3 means we don't need to make more than 3 comparisons. But notice here, each of these are its own t-test. Okay. And each of these t-tests has its own alpha. So, for example, with our first test, we have our own alpha at, let's just make it 0.05. And let's pretend the question is whether the group has a higher body temperature than 36.5 degrees. Okay? So we're going to make this a one-tail test or a right tail test. Okay? Again, right now, which tail it is does not matter for this. We are interested in the alpha. Again, alpha is the probability of a type 1 error. Okay? So here, alpha is set at 5% or 0.05. And we have 2 more of these to go, don't we? So I put alpha 1. Here is alpha 2 at another 0.05. So that's another 5%. And the third one here, we'll do one more time. Another alpha for the third pairwise comparison. And here is 5%. Now, each of these tests, okay, has its own test-wise alpha. Or, yeah, test-wise alpha. So here it's 5%, 5 plus 5% plus 5%. And when you add all these up together, okay, so it's 5% plus 5% plus 5%, which is 5% times 3, which is the total of, you guessed it, 15%. So that's our experiment-wise alpha. So our whole experiment, if we do all those tests, is going to be 5% times 3 at 15%, or big alpha equals 0.015, right? Or 0.15, sorry. Now imagine how many tests would you need to make to max out alpha? Remember, alpha is the probability of a type 1 error. And if we add multiple comparisons in the same experiment, how many tests would you need to get the alpha of 100%? And if you're thinking 10 tests, you are right. Well, if we set alpha at 10%, that is, with 5% alpha per test, all you need is 20 tests. And then so you have alpha at 0.05 and then multiply that by 20 and then you get a big alpha of 1, which is 100%. So the whole experiment, taken as a whole, would be wrong all the time. Or at least you have to make the type 1 error, which is rejecting the null hypothesis when there is no difference on test day, 100% of the time with your tests. So think about that. In this case, this is why we have the points here. Each test has its own type 1 error, which is test-wise alpha. So it could be alpha 1 at 0.05, alpha 2 at 0.05, and then here alpha 3 at 0.05. Okay, so if you add them all up, this is the cumulative probability of a type 1 error, or cumulative alpha, which we call experiment-wise alpha. So in this case, with 3 tests, we're adding up alpha 1, alpha 2, and alpha 3, which is 0.05 times 3, which is 0.15 or 15%. Remember, you only need, if each test alpha is 5%, you only need 20 of those to make 100%. So that's where we have this point. Experiment-wise alpha increases as you do more tests. In this case, more t-tests. ANOVA eliminates this problem because we are looking at all the differences at the same time, simultaneously, with only one test. One test. So again, it could be 3 means, 4 means, 5 means, 20 means, doesn't matter. As long as ANOVA can run all those numbers, we can avoid the idea of an inflated experiment-wise alpha. So that's it. That's it for today. We have went over part 1 of our lecture, which is chapter 12, Introduction to ANOVA, and we have looked at the purpose and logic of ANOVA. Okay, remember, so far we have done z-tests and t-tests in our inferential statistics using central limit theorem and sampling distribution for us to approximate the population distribution. And now we're going to use those same techniques, but for multiple mean comparisons. And the only way for us in this particular course at this level right now, one way we can do that is with ANOVA. So stay tuned in the next part as we figure out how to use ANOVA, what are the steps we need, and the post-hoc tests that would come afterwards. So that's it for today. Good luck as you go through these videos, and we'll see you in the next one.